Welcome to the fascinating world of Bayesian inference. Probability is often misunderstood as just a game of chance with dice or coins. However, in the real world, probability is about information. Bayes' theorem is the mathematical bridge that allows us to update our beliefs when new evidence comes to light. It is the cornerstone of modern artificial intelligence, medical diagnostics, and even weather forecasting. Today, we will master this formula by solving two practical, everyday problems that will change how you perceive certainty. Let's break down the formula. P of A given B is what we call the posterior, the probability of an event happening given that another event has occurred. This is equal to the likelihood, P of B given A, multiplied by our prior belief, P of A, all divided by the total probability of the evidence, P of B. While it looks like a simple algebraic expression, it represents a deep philosophical shift. Your initial knowledge, the prior, must be adjusted by the strength of the new evidence. According to statistics from the Bayesian perspective, nothing is 100% certain. We only have degrees of belief that evolve. Exercise 1, the medical paradox. Imagine a rare disease that affects only 1% of the population. You decide to take a highly advanced diagnostic test that is 95% accurate, meaning it correctly identifies the disease 95% of the time and correctly identifies healthy people 95% of the time. You take the test and the result is positive. Most people, even some doctors, might intuitively think there is a 95% chance you are sick, but as we will see, that intuition is dangerously wrong. Let's visualize this using a population of 1,000 people. If 1% are sick, that's 10 people. If 99% are healthy, that's 990 people. Out of the 10 sick people, the test identifies 9.5, 95%, as positive. But out of the 990 healthy people, the test incorrectly flags 5% as positive, which is 49.5 people. Now look at all the positive results. 9.5 plus 49.5 equals 59 total positive cases. Your chance of actually being sick is the 9.5 real cases divided by the 59 total positives. The result? Only about 16.1%. This is the power of the base rate fallacy. Exercise 2, the modern spam filter. Every day, billions of emails are sent. Statistics show that roughly 45% of all global email traffic is spam. Modern filters use Bayesian logic to protect your inbox. Let's say that the word free appears in 70% of all spam emails, but it only appears in 2% of legitimate ham emails. If you receive an email containing the word free, what is the probability that it is actually spam? We define our prior P of spam as 0.45, the likelihood P of free given spam as 0.70. The probability of seeing free in a legitimate email P of free given ham is 0.02. To find the denominator P of free, we sum the weighted probabilities of both scenarios. When we plug these into Bayesian's formula, the probability that the email is spam jumps from 45% to over 94%. This significant increase shows how a single piece of evidence, the word free, drastically updates our confidence level. To conclude, Bayesian's theorem is more than a formula, it's a mindset. It teaches us to be skeptical of striking evidence if the prior probability is extremely low, and to be decisive when evidence is overwhelming. Whether you are a data scientist building neural networks or someone reading a medical report, remember, always update your priors. References: Sheldon Ross, A First Course in Probability; Andrew Gelman, Bayesian Data Analysis; E.T. Jaynes, Probability Theory, The Logic of Science.